Gnanam paramam dheyam. Knowledge is supreme.
Alright. So, we are discussing electronic spectroscopy. Today, let us talk a little bit about what electronic spectra actually look like and what is it that we can learn from them. This part that we discussed in the next half hour and so is best learned from Banwell's book. It is not anything difficult. What have we learned so far? We have said that we are working under this Born-Oppenheimer approximation, which says the total wave function is given by psi Es multiplied by psi V multiplied by psi R, where V is vibration, R is rotation, E is electronic, S is spin. So, we are writing the spin orbital wave function together, but of course, we can split it into psi E into psi S. In fact, we did that when we talked about transition moment integral, and we wrote the transition moment integral finally as integral psi V dashed psi V. While doing it, so far we have neglected psi R. Today, in fact, we are going to talk about effect of rotation, but then we will not derive the selection rule for it. You can try and derive it yourself, but not today, maybe a little later, multiplied by psi Es, maybe psi E dash mu psi E multiplied by psi S dashed psi S. Transition moment integral has to be non-zero for a transition that takes place. So, we said that this factor is not necessarily 0 because psi V and psi V dash are wave functions from different electronic manifolds, different vibrational manifolds, different electronic states. What is this called? Frank-Condon factor. Very often it is written as chi. Of course, it might be a little confusing for us because we are already using chi for character and we are using characters very frequently, but as you know the same symbol is often used for different quantities. So, please remember that chi is also written as a symbol for Frank-Condon factor. So, what Frank-Condon factor does essentially is that it modulates the intensity of transition, right. But what determines whether the transition will take place or not are these two, this integral and this one. If this is non-zero, that gives rise to the orbital selection rule, and if this is non-zero, that gives rise to the spin selection rule. In fact, we have already derived one of them. What is the spin selection rule that we came up with? From here we had got delta S is equal to 0, but we also got something else, something that is not actually written in any of these books that we study. What is it that we got? Yes, I mean got means I just told you and then I asked you to satisfy yourselves that delta ms is also equal to 0. This is a condition. Total spin angular momentum does not change. Z component, what does ms stand for? It stands for the z component of total spin angular momentum. So, z component also does not change. This is the spin selection rule, and spin selection rule is the most stringent of all. So, spin forbidden transitions are really weak if they are at all seen. Orbital selection rule, as we will see in the next couple of classes, there are ways of bypassing the orbital selection rule. And one of the orbital selection rules that you know already, somebody asked me in the last class, is Laporte selection rule. d orbitals. If both are d orbitals, both are centrosymmetric, and this mu is not centrosymmetric and it is antisymmetric with respect to inversion. So, the triple product is antisymmetric. That is why it the DD transitions are orbitally forbidden, but then they can take place, because what you can do is you can have a coupling between vibration and electronic motion. So, that is called vibronic coupling, as we are going to study. Due to vibronic coupling, it is not always impossible to bypass this orbital selection rule. So, as we are going to study in the next couple of days, vibronic coupling can actually give you bands that are otherwise forbidden orbitally. Spin selection rule is more difficult to break. How is spin selection rule? How can you work around spin? Well, you cannot work around. How do molecules sometimes work around spin selection rule? Yes, by what is called the spin orbit coupling. So, if you cannot write like this, if you have to continue writing psi es, then you do not have this integral coming out. Okay? So, that is called spin orbit coupling, and in fact, I should modify what I just said. You can work around this as well, because the spin orbit coupling integral, the interaction integral, that has a term in mass. So, if you bring in a heavy atom, then you have greater spin orbit coupling, and so transitions that otherwise do not take place can take place, right. So, this is where we are. This is what we will deal with once we talk about symmetry of states. Before that, let us finish the discussion that we were having about diatomic molecules. Okay. Let us focus on this, the Franck-Condon factor. As we have discussed briefly, Franck-Condon principle requires transitions to be vertical. Vertical means x axis is internuclear distance. So, internuclear distance does not change during an electronic transition. The basic idea is the same. Nuclei are heavy, electrons are light. So, when you have electronic motion, in that time scale you cannot have nuclear motion also. So, this is your Franck-Condon principle. So, the other thing that we have discussed briefly, or some of us may even know, is that we can have different situations. The way I have drawn it here, the equilibrium bond length, how do I know what is equilibrium bond length? Internuclear separation at which we get the minimum. So, it is possible that the equilibrium bond length is exactly same for ground and excited states, then this is the situation. Then Franck-Condon factor is actually maximum for the 0,0 dashed combination. See, most of the transition will take place from the center, right, because that is where psi star is maximum. So, in this case, the spectrum is expected to look something like this. This here is the 0,0 dash transition, this may be 0,1 dash, this may be 0,2 dash, this may be 0,3 dash, so on and so forth. Remember, dashed indicates a vibrational level in the higher upper electronic state. Which way does energy increase? This way or this way? 0,0 dash, 0,1 dash, which one has higher energy? 0,1 dash, right. So, energy increases this way. I can write like this, nu bar increases this way, let us not forget that. What happens when the situation is something like this? Actually, I have drawn it in the other way, something like this. So, now you see this transition will be the most probable one. So, what is this? 0 dash, 1 dash, 2 dash, 3 dash, 4 dash. So, if this is your 0,4 dash, this is going to be the most intense transition, others will go down 0,03 dash, 0,2 dash, so on and so forth. This way also it will go down. So, that gives you a maximum in the absorption spectrum, and of course, you have internuclear separation, and we have separation between two successive lines due to the separation between the vibrational levels in the excited state. We will have an occasion to come back to this shortly. What happens if the internuclear distance in the excited state is smaller than the internuclear distance of the ground state? Same thing happens. you still go through a maximum. And then the situation is this, now a vertical transition from the center takes you to a state which corresponds to a dissociated state. Okay. That is something that will cause dissociation. So, what will happen is you have so now nu bar increases this way. I will draw it the other way. I am drawing nu bar to be increasing from right to left. So, I will draw it that way. So, this is exactly a flipped image of what you see in Manuel's book, and then you have a continuum. Because once you have excited beyond the dissociation limit, then of course, you get a continuum because your atoms can move with whatever kinetic energy that is there. So, this is called, this nu bar where this continuum begins is called the dissociation limit. Okay. Let us see what this dissociation limit is. This is your dissociation limit, right. Let us say up to this. This I will say is E dl. Maybe I will write epsilon dl, so that we remember everything is in centimeter inverse. Now, what is this energy? This is something that we have studied when we talked about anharmonic oscillator. What is this energy? What does that mean? How do we write it? We write d0, isn't it? Right? That is the energy that you have to provide to take your molecule from V equal to 0 state to such a V state that dissociation occurs, okay, in ground state. So, what is this then? That is also some kind of d0, right. That is also d0, but not for the ground electronic state, for the excited electronic state. So, we will write it d0 dash. Okay. One more thing that I want to draw is this. What kind of a transition is this one? V equal to 0 to V dash equal to 0. We will call it epsilon 0 0. This is called the band origin. Are we clear with the definitions? Now, let us see what do I get when I add one of these quantities to another quantity. What do I get if I add, say, epsilon 0 0 to d0 dash? Epsilon 0 0 to d0 dash, what do I get? Yes, epsilon dl, right, dissociation limit. So, if you are in your spectrum, if the dissociation limit is very well defined and if 0 0 dashed transition is also very well defined in your spectrum, then in principle you can decide what is d0 dashed, right. But the problem with this approach is that neither of these is usually very well defined. So, when you have something like this, you can see that intensity is going down, right. So, 0 0 dashed is going to have a very small intensity here. Sometimes what happens is the intensity is so small that you do not even see it very well, alright. And dissociation limit is also something that is fuzzy. It is not so easy to see where exactly dissociation limit has begun. So, if we use this and try to find out d0 dashed, then we will perhaps get only an approximate value of d0 dashed, okay. So, but there might be little better ways, okay. Which way? One thing I could perhaps write is this. Let me write this. What is this energy? Let us say I have a molecule AB, right, and then upon dissociation I get A and B. What is this energy? What do I have here in this situation? What do I have here for this internuclear separation? I have AB, the molecule. What do I have here? A plus B. What do I have here? A plus B. And who's giving me the answer? I cannot. You gave the answer? Okay, right. Yeah. So this is excited state of the product, right? So this is something that you can actually measure using say calorimetric measurements. So what you do is you take the atoms, right, and see what is their excited state. You can get it even thermochemically. So this epsilon Ex is something that is that is something that you can measure directly and accurately. So now if I rewrite, if I reformulate, what do I get? What is D0 plus epsilon x, epsilon Ex? What is that? I can write this like this, epsilon Ex plus D0. Now for a situation where I do have a continuum in the spectrum, now I am a little more comfortable because that gives me more parameters to play around with. Suppose I can know this experimentally. Is there any way in which I can determine D0, some other experiment? How do I find D0? See, usually you are right, there is no point in thinking you will not be right. So remember what we had discussed for anharmonic oscillator? If we look at 3 lines, right, what are the 3 unknowns that we have? One is anharmonicity constant, one is D0 and one is this equilibrium vibration frequency. So if you just have the position of 3 lines, then you have 3 equations, 3 unknowns. So if you look at the IR spectrum, then you should be able to determine D0. So one thing you can do is, this you measure thermochemically, you can measure this, you can find a value of this using IR spectroscopy, and from there you can find out the dissociation limit. Once you have dissociation limit, then if band origin is not very prominent, you can find out band origin if D0 dash is known. If otherwise, we got a problem. So once you know this, then it becomes you have a little more you have a little bigger field to play in. But things becomes really interesting when you don't have a dissociation limit at all. Suppose we have this kind of a spectrum, then what happens? Is there a dissociation limit here? There is no continuum. Can we find out the values of D0 or D0 dash or something from there? Actually we can. For that, what we will do is, we will write the second part of this discussion. Of course, we will neglect rotational levels for now. In Born-Oppenheimer approximation, we write the wave function as product of the wave function, product of electronic and vibrational wave functions. How do we write the energy? Sum, right? Separation of variables, sum. So what we can do is, we can write psi EL is equal to psi, maybe psi is equal to psi ES plus epsilon is equal to epsilon ES plus epsilon V. Okay. So if this is the case, then what is my delta epsilon? When I go from this level to this level, delta epsilon would be epsilon 0 0 plus delta epsilon V. Do we agree with that? I go from it is easier to draw like this. This is V equal to 0, 1, 2, 3. This is V dashed. So, 0 dashed, 1 dashed, 2 dashed, 3 dashed. Let us say I have this transition. Okay. What is the energy of this transition? I am saying this is delta epsilon. What is delta epsilon? This here is epsilon 0 0. Once it is needless to state once again that all upward transition has to begin at V equal to 0, right. Only V equal to 0 is populated at ground state. So, delta epsilon, this is epsilon 0 0 plus what? Plus what? This. I can call this delta epsilon V. Is that right? What? That is not right. Vertical transition, yes. No, intensity may be different. Intensity is going to change, right? This is the intensity, but position will be there. Vibration energies will be a little different from here to here because the bond is weaker, right. So, usually the vibration energy is also different, but I have written it here delta epsilon V. What is the problem with that? Yes. No, so what we are doing is we are breaking it down into two parts. One we are doing 0 to 0, right, and then from there we are saying it is delta epsilon V. Now, we will write the expression epsilon 0 0 dash plus what will it be? What is delta epsilon V? What is epsilon V? V plus half into nu bar, I will write nu bar V multiplied by Xc. Of course, we are considering it to be an anharmonic oscillator, right. The potential we have drawn is kind of a Morse potential, has to be anharmonic. So, nu bar V Xc minus, you have to help me with that, Xc will not be there, fine. Then V plus half whole square Xc nu bar V, that okay, right, minus what? Minus V equal to 0. So, are you now satisfied? We are taking the same Xc, same nu V, everything same. So, you put 0, you put half nu bar V minus V plus half whole square Xc nu bar V. Okay. So, let us put V equal to 1, what do we get? If I put V equal to 1, what do I get? So, this becomes what? Sorry, V equal to 0, fine. What happens when I put V equal to 1? 3 by 2, what is this? 9 by 4, what is this? Maybe I will open the bracket 1/4. What do I get then? Nu bar V minus 2Xc nu bar V. Are we okay with this? What happens if I put So, this is I can say epsilon 0 1 dash. What happens if I put epsilon 0 2 dash? What will I get? Epsilon 0 0 plus yeah. Okay. Let us do it a little differently. Can you tell me? I take 2 0 to v dash and 0 to v dash plus 1. You can work out the expressions for that. Let us do it. Let us work out the expressions for 0 to v dash transition and 0 to v dash plus 1 transition. What will it be? So, essentially this is what I want to work out. Can you tell me what is the expression for delta epsilon? I want to work out the expression for epsilon 0 to v dash plus 1 minus epsilon 0 to v dash. What do I get there? So, v dash plus 3 by 2 into nu bar v minus v dash plus 3 by 2 whole square x c nu bar v. From that you have to subtract v dash plus half into nu bar v minus v dash plus half whole square x c into nu bar v, right? What is the expression? Something like this, nu bar v 1 minus 2 x c v dash plus 1, something like this, right? This is what we get. What is this delta epsilon? What is delta epsilon? Delta epsilon is the separation between two lines in this spectrum or this spectrum, right? This is delta epsilon, isn't it? We will draw it a little better. One of these separations is delta epsilon, all right. So, what happens if I plot delta epsilon against v dash? What kind of a line do I expect? Yes. Yeah, it was kind of stupid of me because I said what kind of a line do I expect? We expect a line, well, positive slope or negative slope? Negative slope. So, this is how, and of course, do not forget that v is discrete, right. So, you expect this kind of a decrease, all right. So, one thing we can do is this, we can just extrapolate, draw a line and draw it until it cuts x axis. If I work out the area under this curve, what does that area give me? You understand what I am saying? You told me you are going to get a line with a negative slope, right. So, if you extrapolate the line from y axis to x axis, you are going to get a triangle, a right angle triangle. It is very easy to work out the area under the triangle, okay. What does that area give me? Okay, let us say I just take the first 2 points here. What does this area give me? Fine, let us look at this now. This is one delta epsilon, this is the next, this is the next, this is another delta epsilon. If I add them all up, all the delta epsilons, does that give me the area under the curve? Right? That is delta epsilon versus v, right? So, if I just add up all the delta epsilons, that should give me the area under the curve. So, if I add up all the delta epsilons, what does that give me? This is one delta epsilon, this is another, so on and so forth. So, if I add them all up, what do I get? I do not get dissociation limit, I get D0. But which D0? Ground state or excited state? Excited state, right. So, this area, the entire area is going to give me D0 dash. In excited state also, we are taking the anharmonicity constant to be the same. Where have we done that? Anharmonicity constant is so small that variations in that are negligible. Okay. So, this is one way of finding D0 dash even if you do not have dissociation limit. Any spectrum should be able to give you that, and this kind of an extrapolation is called a Birch-Sponer extrapolation. You can study it from Manuel's book, you can also study it from Macquarie and Simon's book, both have it. Alright. So, once you have D0 dash, then what can you find out? Suppose I do not have a dissociation limit in my spectrum, but in this way I have found D0 dash. Epsilon 00 dash is there, D0 dash is also there. So, epsilon 00 dash plus D0 dash will be equal to D0 plus epsilon Ex, right. So, from there, so this is what I am using now. What are the things that I know already? As I told you, epsilon Ex can be found by non-spectroscopic experiment. D0 is something that you can know using your IR spectrum. D0 dash you have just determined. So, if your band origin is not very prominent, then you can find out band origin. That is one thing, but the bigger application is if you know band origin, you can find D0 also. Now, tell me, suppose I know the band origin, I determine D0 this way. Is it better to find D0 this way, or is it better to find D0 using IR spectrum? Actually, there are pros and cons. There are factors that tell you that finding D0 using electronic spectrum is better, but there are factors that make determination of D0 from the vibrational spectrum better as well. Okay. What are the factors that favor determination of D0 from electronic spectrum? What are the factors that favor its determination from vibrational spectrum? What is the problem of determining D0 from electronic spectrum? What would be the problem? The problem would be resolution. IR spectra of course are recorded at higher resolution than electronic spectra usually. So, if you want to make an electronic spectrometer that has sufficient resolution to give you information about vibrational levels, that is a more difficult proposition. So, resolution is the problem in determining D0 here. What is the advantage? The advantage is if you do it from your vibrational spectrum, then you essentially, how many lines do you have? You have fundamental, you have first overtone, if you are lucky you have second overtone, nothing else, at most 3 points, right, at most 3, and in the third one the intensity is so less that errors creep in there. Here in electronic spectrum usually you get you can look at more levels. Okay. So, if you have more points, then of course, it is a little better. Okay. So, these are the pros and cons of determination of D0 using electronic and IR spectra. Okay. One last point, Birch-Sponer extrapolation is linear, right, but if you have, by the way, when I am talking about electronic spectroscopy here, then usually what I really mean is electronic spectroscopy in gas phase, where lines are really very sharp and you get to see a lot of lines. You do this in liquid phase, lines are not going to be so sharp anymore. Lines are broad, and since they are broad, several lines join up, you lose out on the number of lines also. But suppose you have access to sufficiently high resolution spectrum some way or the other, then what you see usually is your expectation is this linear variation. What you see in reality is that you see this kind of a deviation, downward deviation. Why do you think there is a downward deviation? Look at the spectrum, we are plotting delta epsilon versus V dash, right. Straight line is what you expect. If there is a downward deviation, what can cause a downward deviation? Sorry? Anharmonicity, yes, but anharmonicity is already accounted for, right. But anharmonicity is the right answer. See, the thing is, if you remember, what had we said? We had said that this, how do you get the second term in anharmonic, in the expression for energy for an anharmonic oscillator? It is a first order correction term, right. And remember what we had also discussed, that when you bring in corrections, first order correction can come in as a first order term in V. The second order term would be square, third order term would be cubed, and so on and so forth. So, as V becomes higher and higher, then this second order, third order, these terms also become important, okay, and it is always negative. So, when you go to sufficiently high V's, then this is not a complete expression anymore. You have to account for the quadratic term, the term into the power 3, term into the power 4, and so on and so forth. So, what you have is, towards the end you have a deviation. So, that is another advantage. So, that gives you the realistic picture, right, if you go to higher V levels. Neither is this Birch-Sponner linear extrapolation absolutely accurate, nor is the expression of D0 that you would get from anharmonic oscillator. Do not forget, for anharmonic oscillator you get to interrogate only V equal to 0, V equal to 1, V equal to 2, nothing beyond that. So, this higher terms that are there, that actually contribute to D0. Will you agree with me if I say that the higher terms actually contribute to D0? Because when you look at D0, you are looking at this, right. So, you do have several higher vibrational levels coming in. So, who is going to account for that? So, actually, if you have access to sufficiently large number of spectral lines in electronic spectrum, the D0 value determined from there is a little better, alright. So, this is your effect of vibrations on electronic spectra. What you get is, you get a vibrational fine structure, vibrational structure, let us say. The involvement of vibrational levels render a vibrational structure to electronic spectrum. We have encountered something like this earlier when we have when we talked about rho vibrational spectrum. We had seen that there is rotational structure in vibrational spectrum. When you look at sufficiently high resolution vibrational spectrum, you can see rotational structure. Here also, when you have sufficient high resolution, then you see vibrational structure in electronic spectrum. Okay. What is the effect of rotational levels? Can rotational levels also have some effect? If you have really high resolution electronic spectrum, then the rotational levels should also give you some what is called fine structure. Fine structure due to rotation is seen in vibration in electronic transitions as well, right. So, I am not going to derive the expressions there, because actually we have done that derivation already once. So, what is the real picture? This is on electronic level, these are the vibrational levels, each vibrational level is associated with rotational levels as well. So, when we say that the transition originates here at V equal to 0, what I really mean is that the transition originates in different J values, J levels, alright. So, some selection rule is associated with this as well. Once again, we will not derive the selection rule now. Once we are done talking about symmetry of states and derivation of whether transition moment integral is 0 or not for electronic levels, maybe we will come back to it. So, the selection rules you have are, well, we are talking about once again diatomic molecules, delta J equal to 0 for singlet sigma to singlet sigma kind of transition. Greek and Latin, if not Roman, right. What is this small 1 large sigma? We are going to learn in detail tomorrow onwards. What this one means is, this is not read as 1 sigma, it is read as singlet sigma. The small 1 subscript, that gives you the multiplicity of state. Sigma gives you the symmetry of state. For now, just believe me that the ground state is always singlet sigma for all molecules, in which you have spin pairs. Okay. We will elaborate upon this a little bit later on. Those of you who have studied LS coupling and all would perhaps already know that the ground state is singlet sigma. So, this is the selection rule, delta J equal to 0, no, what am I writing, sorry, delta J equal to plus minus 1 for singlet sigma to singlet sigma. For all other transitions, I think it is delta J equal to 0 and plus minus 1, provided this delta J equal to 0 transition does not take place for this J equal to 0 to J equal to 0 to, we will write it like this, J double dash equal to 0 to J dash equal to 0. This is forbidden. For all other J values, delta J equal to 0 and plus minus 1 for all electronic transitions other than singlet sigma to singlet sigma. Okay. Now, when you do this, you have to account for the rotational levels as well. So, what will the expression be? Again, delta epsilon, which is nu bar, will be nu bar, what should I write it? I will write EV, is that okay? Whatever expression we have got earlier, that is involving electronic and vibrational levels, whatever that expression is, plus you will get delta B J into J plus 1. Makes sense? We know already that vibrational energy of jth level is B into J plus 1, delta B into J plus 1. So, the question is B the same for ground and excited states or is B different? Usually it is different. Is it larger, is it smaller? Smaller, why do you think so? Oishani? You did say smaller, didn't you? So, why do you think it is smaller? Okay, you are right, but just tell me why. Who wants to defend that B is smaller in the higher electronic state? Why is B, when is, okay, let me change the question. When is B smaller in the excited state? Yes, Daksha? Why? B is inversely proportional to R square. So, the equilibrium bond length is greater, you are right. So, now the thing is, if the transition is such, so this is where the qualifier comes in. B in excited state is smaller than B in ground state, when obviously the R is greater, right? Well, rather R square is greater. So, if you have a transition that weakens the bond, then R will be greater, equilibrium bond length will be greater, right? So, if I think it is something like let us say ethylene, there is a pi star transition. What has double bond in the ground state is a single bond in the excited state, right? So, bond length should increase, equilibrium bond length, that is when B should be lesser. But it is not necessary that all transitions in all kinds of electronic spectroscopy will weaken the bond. there can be something that strengthens the bond also, right. So, charge transfer transition, right. In that case, it will be the other way around. So, the crux of the matter is that B is going to be different. So, when B is different, have we encountered a situation like that, where row vibrational spectra once again, what was the expression we got in that case? We got something like B dash plus B multiplied by J plus 1, then plus or minus B dash minus B, I think, into J plus 1 whole square. We get the equation of a parabola. So, what you get is, you get equations of parabola in all the cases. In this case, what kind of a band is it? When delta J equal to plus minus, when delta J is 0, plus minus 0 of course, when delta J is 0, what band is it? What do we call it? We had a quiz or mid-sem question on that. A, B or C, which band is it? Neither A nor B nor C, right? Neha says it is Q. Is she right? Q band. And what is delta J minus 1? What is it? P. And delta J plus 1, the only choice left is R, right? So, remember P, Q, R. So, you understand that in this case you are going to have PR structure, in this case you are going to have PQR structure. But PR and PQR structure are actually interesting in this case, because you have a parabola. So, what you have is, you have this lines going to higher energy or lower energy and then turning back many times. Okay. So, please read this part from Manuel's book. Tomorrow we are going to just, so that is what I had drawn here, the parabola. So, if you see, this is J, these are the J values, these are obviously J plus 1, column C is J plus 1. So, this one is 19 into A1 plus 1, well A1 plus 1 is just C, minus A1 plus 1 whole square. So, the way I have drawn it is this, I have taken B dash and B to be 9 and 10 respectively, right. So, 19 is B dash plus B, this is your well B dash minus B. If this is the scenario, you get this kind of a parabola. So, see what does each point indicate? Each point indicates the position where the line occurs, alright, in terms of this B and B dashed. So, what you see is it keeps decreasing. Now, for one of the lines P or Q, this becomes minus. So, please read this part from Manuel, you will see that you get the same kind of expression as what we got for row vibrational spectrum. We get this some constant multiplied by P plus some constant, well some constant multiplied by P square, where P can be plus or minus. So, when this is minus, no, I am making a mistake, I will show it tomorrow. So, there you see that it turns, and the place where it turns, that is called the band head. So, tomorrow maybe we will quickly demonstrate this to you and then go on to discuss symmetry of states, which will allow us to talk about the transition moment integral.